give you an introduction. So next up, we have Indranil Ghosh to present Introducing Lambda Calculus in Python. He's a final year master's student in the Department of Physics from Jodhpur University in Kolkata, India. Please make him welcome for this talk, and thank you for waiting through the technical issues.
Hello, everyone. So today I'm going to introduce Lambda Calculus with Python. This talk actually introduces some basic concepts of Lambda Calculus along with some hands-on practice and implementation of the application of using Lambda function with Python. So this would be basically helpful for students who have a background in either mathematics or computer science or physics. So yeah, so I'll be trying to cover most of the parts. So I would like to first introduce the basic theoretical concepts like abstraction and application in Lambda Calculus, along with some substitution, what is a substitution. Then I would mainly cover some data types encodings like Boolean values, logical operators, Church numerals, some predicates, and two recursions. Next, I would like to acknowledge Dr. David Beasley's talk, which actually inspired me to study Lambda Calculus with Python. So I was starting with untyped Lambda Calculus at first. So then I thought, why not go ahead and try these mathematical concepts in Python. So I came up with this talk named Lambda Calculus from the ground up, which Dr. David Beasley delivered at PyCon 2019 Cleveland. So I would also like to express my sincere gratitude to the PyConline AU 2020 organizers. They have tremendously helped me to make this talk possible. So for assisting me in all kinds of stuff. So okay, so I will start with some history. So at first, this Lambda Calculus was started by Alonzo Church while he was teaching mathematics and philosophy at Princeton University, and the motivation behind the study was to study some mathematical properties of computable functions. So there is some controversy regarding the choice of the lambda symbol, why Church came up with this symbol or why the name lambda was chosen, but he stated later that it was completely accidental, no controversy regarding that. So some notes to remember, like Lambda Calculus is able to simulate any Turing machine, making it Turing complete. It lies in the heart of functional programming and has other pertinent applications in philosophy, category theory, or computational linguistics. Lambda Calculus is simulated in some functional programming languages like Lisp, Scheme, Meta language, or Haskell. So Haskell is, Lisp, Scheme, and Haskell are very popular, but some of you guys may have, heard about Meta language, ML. So the basic fundamental thing about Lambda Calculus is that functions are actually values. So these are this line we should keep in mind, that functions are actually values. So in our study, we mainly focus on the untyped Lambda Calculus, and we use Python 3 as our programming tool. So although not a purely functional programming language, Python has had Lambda functionalities added to its syntax during 1994. So we all know what a function is. So I will start with introducing a function. So a function f is a binary mapping which relates to values. Like it's a binary mapping from a set of inputs x, which is called domain, to a possible set of outputs called y, which is called codomain. But each input actually corresponds to exactly one output. So one value in x can be mapped to only a single value in y. So like if we define this fx equals to x plus 1 whole square, and where f maps x to x plus 1 whole square, and so we can go to examples like f of 5 is actually 36. So 5 is mapped to 36, only a single value. So it's not possible that any other value will be mapped to 36. So only 5 can be mapped to 36. Similarly, 2.7 can only be mapped to 13.69, and so on. So this function fx equals to x plus 1 whole square in Lambda calculus form can be written in this expression. So lambda symbol x separated by a dot given by x plus 1 followed by x plus 1 whole square. So this dot is the separation symbol, and the term after the separation symbol is the expression. So here x is the domain, x specifies the domain, and x plus 1 whole square specifies the codomain. So this dot is the separation symbol, and tells that after the separation symbol is the expression to which the input x is mapped. So x is mapped to x plus 1 whole square. So this is the basic thing to keep in mind. So I chose a example to make it more clearer. So now to pass an argument like 5 or 2.7, like we did in the basic function example, like here. F of 5 equals to 36 and f of 2.7 equals to 13.69. We can do the similar thing in lambda calculus in the following way. So like the first term, like the first one, fx equals to, f of 5 can be actually written as this. So lambda x dot x plus 1 whole square followed by another parenthesis which takes in the argument. So 5 is the argument which is passed to lambda x dot x plus 1 whole square, or in this case, or the second case, lambda x dot x plus 1 whole square 2.7. So the expression inside the first parenthesis is the abstraction, and the whole expression, only this expression is called the abstraction, lambda x dot x plus 1 whole square, and the total thing taking in the argument together is called an application of the function. In Python, we can do this in a very similar fashion. Like suppose we want to simulate the square function. So like lambda x dot x square taking in 9 as an argument. So is written in Python as lambda. So very similar analogy, like lambda is replaced by the lambda call lambda separated by a space. Here we see that there is no space after the lambda, but in Python we should give a space here. The syntax is prepared like that, and here this x is the this is the domain. The separation symbol dot is actually replaced by a colon here. So and the x square is written in as x square, like we do in Python. So and 9 is passed as an argument. We will see that 81 is the result. So as theory tells us. So we have already seen what an abstraction and application is. So a new expression lambda x dot a can always be generated from an from an expression a and a variable x. This is called abstraction. And a new expression a applied to b is called the application of the expression a to the expression b. So we can also try this with two lambda functions in a single expression. So like lambda, so we can pass lambda x dot x square plus y square. So it is a this total is a function of two variables. So this is actually f of x comma y equals to x square plus y square. So this can be written as lambda y dot lambda x dot x square plus y square. So it is taking in two variables. So yeah, so applying this to the so at first we apply argument. So we passed 2 as an argument to the whole expression. So we will see that all the y's are replaced by 2 at first. So this will be evaluated to lambda x dot x square plus 2 square, substituting the y variables in the expression. This is actually the beta reduction. So when the reduced lambda function is subjected to another application, like we pass 3 as an argument, all the x's will be replaced by 3, and so we will get 3 square plus 12 square equals to 13. So the whole expression is like this. It's written like this. So we pass 2 as an argument first, then we pass 3 as an argument later to the previous thing. So in Python, we see that this is the expression, and in Python, in similar way, we can express this. So lambda y colon lambda x colon x square plus y square, with 2 as the first argument first, and followed by 3 as the second argument. So we'll get 13 as theory says. So we can also try our hands on with other applications, like the application of, so we can pass another lambda function as an argument to some other lambda function, so which after substitution becomes, so this is actually the identity function. So lambda x dot x applied to lambda y dot y. So this becomes we'll see that this becomes lambda y dot y. This is the identity function. So we can also try this out in Python. So lambda x dot colon x followed by lambda y colon y applied to this, and we'll get, if we pass 5 as an argument to L, so we stored this function in L. So and then if we pass 5 as an argument to L, we'll get back 5. So a constant function is, so we can also define a constant function like lambda z dot c. So it is like whatever argument you pass, it will always return z. So like lambda z7 with 3 as an argument passed to it will return 7, and similarly if we pass lambda y dot y to this lambda z dot 11, we'll get 11. So this is the so we saw this lambda y dot lambda x dot x square plus y square, and this is actually called the curried version of f x comma y equals to x square plus y square. So it was named after Haskell Curry, after whom the programming language Haskell is also named. So he was a pioneer in combinatory logic. So this can so f of x comma, so this can also be written in lambda. So with using lambda, so lambda x comma y colon x square plus y square with 3 comma 2 as 2 arguments passed to it, it will return 30. So I am already, I think, out of time, but so I will keep some theory. So like any valid expression in lambda, so I will tell what a lambda term is. So any valid expression in lambda calculus is called a lambda term. So we saw here like so here like y or x are variables, so any variable is a lambda term. Also the abstraction is also a lambda term, so like lambda x dot a, and also another application can be called as a lambda term. So we'll keep in mind what a lambda term is. So I will skip this theory. So I will also tell there are 3 kinds of variable occurrences in a lambda term, like binding, free, and bound. So if you go through the slides, you will get the idea. So the slides will be online. So I'll try to skip this. Yeah. So now I will tell what a combinator is. So combinator is a term whose free variable is actually a null set. So if we study free variable, you will understand that. But this is the basic thing. Like in the free variable of a lambda term, if it gives a null set, it's a combinator. So the identity function we saw before, it's a combinator, and we can also define another combinator like b combinator. So b is actually written as lambda u v w dot u applied to v applied to w. So this lambda u v w is actually the short term for lambda u dot lambda v dot lambda w. So we can also show that b is a combinator. So if we find out the free variable of the b combinator, we will get a null set. So the mathematics is very simple. So like you can get the idea. So we can define this combinator in Python, like b combinator like lambda u dot lambda v dot lambda w with the u applied to v applied to w. So if we pass b, we will see that it's a function. So we can also define a k combinator, like k equals to lambda u dot lambda v dot w, and similar way in Python. So the behavior of k is to choose the left argument if 2 arguments are passed. Like if 1 and 2 are passed to k, we will get 1, and if 2 and 1 are passed to k, we will get 2. So it picks up the left element. And we can also define another combinator like C combinator. So C equals to lambda u v w, like lambda u dot lambda v dot lambda w dot u v and w. So these are different combinators we can try with Python. So I will skip this reduction part. We already saw what a beta reduction is. So yeah. So like now we'll encode some data types and church numerals. So like true and false value. So true can be written as lambda u dot lambda v dot u. So it is also called the t combinator, equivalent to the k combinator we saw above. So it will always it acts as a switch, as told by David Beasley in his talk. So I got this term switch from his talk only. So like yeah, so it was like the behavior of true is to actually choose the left element, as we saw in k combinator. So if 2 arguments are passed, 2 elements are passed as arguments. And for the false, we will write lambda u dot lambda v dot v, and the behavior of false is to actually choose the right element. So if we pass 1 comma 0 to false, it will choose 0. So like the similar way we can go with not, like lambda u dot u false and true. And also with and, like lambda u dot lambda v dot u v w. So we can go defining this in lambda calculus with lambda function in Python. So very trivial. So we can we need to remember these things, and we can go with trying simulating the behaviors of all these logical operators. So like we can also go with or and if then else. So next we'll try encoding some numbers called church numerals. So like 0 is actually written as lambda f dot lambda u dot u, and 1 is actually written as lambda f dot lambda u dot f of u. So to understand the behavior, we actually need to define a plus 1 function which will return, taking in an argument n, it will return n plus 1. So it's a very trivial function. So like to understand the 0, if we pass 0 alone, it will return as a function. So but if we want to understand the behavior of 0, we need to pass plus 1 and 0 as arguments to it. Also for 1, we need to pass plus 1 applied to 0 as argument, so it will return 1. For 2 also, if we write 2 plus 1 and 0, we'll get 2. We'll get back the 2 integer. So I'll move on. So like we can also define successors, addition, multiplications, and powers. So we can define so we can define some tuples. Like tuple can be replaced shown by lambda u dot lambda v dot lambda f dot f applied to u and v. So we can go with tuple, we can go with left, we can go with right. So left will indicate the left element of a tuple, right will indicate the right element of a tuple, and empty will give us an empty list. So we can define predecessor, subtraction, and also we can check this predicate if a number is 0 or not. So we define is 0, and then we check is 0, and if we check 0 is a 0 or not. So is 0 applied to 0, and it's supposed to return true, right? So we already know that the behavior of true is to choose the left element. So it will from 1 and 0, it will return 1 only. So it's working correctly. So we can also check with 1. So is 0 1, 1 and 0, it will return 0. So we can define less than equals to also with this. So the last thing, so I want to define what a y combinator is. So y combinator is written as lambda u dot lambda v dot u applied to v and v, and lambda v dot u v and v. So for a lambda term, so we saw what a lambda term is. For a lambda term a belonging to so for a lambda term a, y combinator applied to a is a fixed point of a. So this is the behavior of y combinator. So this is because it can be shown mathematically that a applied to y combinator and a, it will be reduced to y combinator applied to a. So this is like the fixed. So it acts like a fixed point theorem. So. And also we should keep in mind that unlike Haskell, Python does not support lazy evaluation. So to understand fact n and Fibonacci n, so factorial n and Fibonacci n, we need to understand something. So this is like trying to define recursive functions with previous methods will lead to maximum recursion depth error. So we cannot go with like it will try to evaluate all the branches of the encodings parallelly at the same time. So we need to redefine.
We're just a couple of minutes over. If you can wrap up at the end of the slide.
Yeah, I have only three more slides, so I will wrap up this. Is that fine?
Yep. Just
okay. Yeah. So we need to redefine some previous functions by adding extra function calls. Like before starting to encode. So like we defined true before, but to work with Fibonacci or factorial n, we need to define true new as lambda u, lambda v. And u should be passed as a function. Similarly, for false, v should be passed as a function. And is 0 new would be defined like the false and the true should be replaced by false new and true new. And the y combinator, as we defined before, like here, we will define that with lambda function in Python. So to understand the factorial n, we will define n1 at first. So n1 is lambda f, lambda n. 1 if n equals to 0, else it will return n into f of n minus 1, as we do in factorial n. So now to understand, to find the factorial of a number argument n, we will pass y applied to n1 to that. So like y n1 applied to 6 will return 720. So 6, the factorial of 6 is 720. We know that. So y applied to n1. So y is the y combinator here. Applied to n1, applied to 6 will give 720. And the last thing, like for Fibonacci, so to find the nth Fibonacci number, like we define n2 equals to lambda f, lambda n. It will return 1 if n less than equals to true, else it will return f of n minus 1 plus f of n minus 2, like we do in Fibonacci case. So again, y combinator applied to n2, applied to 9 will give 34. So yeah, so this is the 9th Fibonacci number. So okay, so here are the references. That ends my talk. Thank you.
Great. Thank you so much for your talk on Lambda calculus and Python, Indranil, and thank you for handling
Thank
the
you,
technical
Caitlin.
difficulties so well.
Thank
Next we have
you.